Nice to see all of you again. For people that somehow this is their first time coming, I'm Anthony, and this is actually the last out of 8. And this is a lecture series from the Enrico Fermi Institute, the Arthur Compton lecture series. And so today we're going to be talking about big picture. So last time we zoomed out a little bit to talk about everything we've seen pieced together into analysis. And today we're going to go even bigger picture. But I want to start off kind of how I do it in other times and put some interesting readings on the board with a very late edition actually by Van, which is this YouTube channel by someone named Don Lincoln at Fermilab, and it has really, really great videos about all sorts of very hard things in physics. I go and watch these videos time to time to learn better science communication and all sorts of things. And then the other ones I'm kind of linking, not because you would have heard about them in the past, but because things that we'll talk about today, if you want to learn more, these are good references. So first, there's this report that came out end of last year, where every 10 years the particle physics community comes together and makes a decadal plan. And so this kind of lays out the big visions for the field and across all different areas. And so I think the document is something like 50 to 100 pages. But then there's an executive summary that's maybe like 2 pages, and you can read it and understand a lot of where the visions are going. So that's on the physics side. And then on the machine learning and kind of the hardware side, this is an article that I'm reading right now. It's by someone named Dario Amati, who's a CEO of a company called Anthropic. And so he was one of the first people that were doing these large models and understanding dynamics of them. And then this book is something that I learned a lot about chips and the large international projects that are required to actually build these type of hardware. And then kind of for people who are like me and like just looking at kind of weird, wild technology that people are doing all over the internet, this is a kind of a blog type thing, a little bit like Reddit. I don't condone everything that's on there. I don't say that everything is trustworthy, but I've learned a lot from reading these things. And so in any case, today what we're going to do is talk about outlook and future directions. And so just as a refresher, what we did last time is we pieced together, or hopefully pieced together, a lot of the different subjects of the lecture series. So we talked about doing tons of collisions, we talked about triggering, we talked about AI, we talked about machine learning and different aspects of the analysis, and we saw how a lot of the different pieces fit together in a recent analysis that was public even just a month and a half ago. And so through this, I hope that you connected a lot of dots. And so this was my first attempt to go from kind of minute details one step higher to at an analysis level. And now we're going to make an attempt to go even one step beyond that and look at big picture and project forward. And so today, when I was making this, I was struggling to make this, and because I was trying to put a lot of ideas from other people in there and where the field was going, and this was very hard for me. So what I decided to do was tell you a very personal view of where I think the field is going, both on the physics side and the AI side. And I'm kind of really going to focus on the future experiments. So I'm going to give you 2 roads that really I see in physics, and then future technologies, mostly focusing on, basically entirely focusing on AI here, but I'll give a nod to other types of technologies. Yeah?
Since the top part is the heaviest particle, is there any experiment that did or are going to smash those together?
Okay, wildly off topic, but yeah. So the question was, the top quark is the heaviest mass particle. Is there any experiment that will smash those together? Currently, no. We don't have a good way. Mostly, the biggest answer is we don't have a good way to isolate individual top quarks because they either decay or exist in bound states. So to get a high density of just single top quarks, we don't know how to do. And actually, I think if somebody came up with that would probably be a string of Nobel Prizes lined up. Okay. But so kind of the breakdown of what we're going to talk about. First, I'm going to give you my view on future physics over the next 5, 10, even 20, 30 years, focusing really on fundamental physics, so particle physics, not really talking about material science or any of the other exciting things. And then we'll talk about future technologies. So first, I want to zone out again to the really big picture that we started with in the very beginning, which was this picture of the evolution of the universe, starting from a moment when everything was in an extremely small amount of space. Then there was a rapid period of inflation, and then the physics that we're talking about really kicks in, so the physics of particles and of nuclei, and then from there the building blocks keep growing and growing together, and then you get the large-scale behavior that you see today, especially as the universe is expanding. And so what we've talked about is how we understand these building blocks themselves. And today I'm going to tell you two different routes about understanding the building blocks better, and then about piecing them together. And so a lot of what we talked about is how we're experimentally testing this theory we have, the standard model, and we've seen that it's very predictive and that it can predict all sorts of behaviors over many, many orders of magnitude. And so from here, if we keep doing searches and everything lines up and we keep doing that, I think the question is reasonable, what's next? And so like I said, I really think that there's two very high-level routes that you go with this. There's one route, which is you have your set of particles or your set of building blocks, and you want to understand the building blocks better themselves. So this is like you have a Lego set and you want to understand each of the Legos together before you try to piece them together. And then the second direction is you actually see if the blocks that you're putting together on the small scale add up to what you see on the large scale. And so that's in essence saying, do what we have here actually, when we run through the billions of years of the universe, give us what we see today on the large scales? And so starting with the first direction, understanding them better, this is something that really has been the essence of what we've talked about for the past 7 weeks or so. And really what we've talked about is these particles here. And from this route of deciding what to do and focusing on this route one, really it boils down to two things. One, you can do precision measurements. You want to go and know, say, the mass of the Higgs boson to the best precision possible, the lowest uncertainty. The second one is you can go and do searches for new physics, like what we talked about last time. And in fact, this is exactly the route that we're going. So I've talked about this in passing quite a few times. So the high luminosity LHC, what this is the LHC right now, the Large Hadron Collider, short for LHC, is in its third run. So we're taking lots of data with it. But then, as we're taking data, there are magnets being shipped. So this is a magnet shipped from actually nearby Fermilab to Geneva. And so this is in a warehouse right on CERN campus. And it contains even more powerful magnets than are used right now. And what this will do, in the next shutdown in roughly 2 years, this will be installed and will ramp up the number of simultaneous collisions from around 60 per bunch crossing to around 200. So we'll dramatically ramp up the rate of collisions. And from that, what we'll do is we'll run for 10 years, roughly. We'll get 10 times the data set size. And then from that, one good figure of merit is we'll get around 400 million Higgs bosons. And so that you can think of as the first direction, measuring things very precisely. And so this is a plot I've showed you kind of in the passing, but this is one of the flagship plots that people will show. It's the different particle masses along the x-axis, the coupling to the Higgs boson along the y-axis, and because the Higgs is what's giving everything mass, it's interesting to measure their coupling. Because if you get deviations in the coupling, that means that large pieces of the standard model could actually be inconsistent. And what you see here is, up to now, what we've done is we've measured the interaction between the Higgs and all of the force carriers. So the W boson, the Z boson, there's actually quarks and photons in here through virtual particles, but we have all of those measurements. And then we have measurements between the Higgs boson and the third generation of matter. So between the Higgs boson and the heaviest quarks, the top quark and the bottom quark, and then between the third generation of leptons, the tau lepton. And then what else you'll see in here is first hints of measurements between the Higgs and the rest of the particles. Yeah?
The bosons that carry the weak force, the W's,
Yeah.
Z's, they have mass,
Yeah.
and that's because of the Higgs.
Yeah.
Okay, so there is a coupling there.
Yeah.
but not to the graviton or to the photon.
Right. So the question was, on here, the W and the Z from the weak force, they have mass, and so there is a coupling there. But then I said that we also measure couplings to, for example, gluons or photons, but they don't have mass, so what are we talking about? Yeah. What we're talking about is actually interactions where two gluons come in, and then they produce top quarks, and then you get Higgs at the end. So I don't usually do this, but because it will be illustrative, we're talking about two gluons coming in, top quarks being produced, and then a Higgs boson coming out. So through intermediate particles, you see.
It's a virtual.
Yeah, yeah, yeah.
So when you say that the Z and the W have mass because of the Higgs boson, does that mean that it's a combination of the Higgs with something else that the Higgs gives mass to? And what would it be if it didn't have the Higgs?
Right. So the question is, when we say giving mass, and we say that the Higgs is what gives it mass, what would happen if the Higgs field wasn't there? Would it have no mass? And then what do we actually, is it just the Higgs field? What we mean is that there is a field, this is called the Higgs field, and the other particles pull energy from that field, and as they pull energy, they acquire mass. And so it's really that pulling of the energy. Now, your other question of would the other particles not have mass? I think maybe the right question is this way we talk about it the right way to talk about it? I mean, we've for sure observed that they have mass. Like the weak force, we know is short range, and everything that we talk about in terms of particles means that there's a W boson that mediates it that's massive. So the question is the way of talking about it with the Higgs boson and the Higgs field the right way to talk about it? And if it were not the right way to talk about it, we wouldn't have seen the resonance at 125 GeV at the LHC. So, because I'll say it would have been very possible that you could have not seen it. And then if we had not seen it, that way of talking would have been wrong. Yeah. Yeah. Good question. So the question, yeah. So the question was, is the pulling of energy from these fields at any way gravitational? At the level we're talking about here, no. We're talking about really just interactions between particles. We're not talking about masses generating forces between them. If we took this analogy and went further and had maybe 2 more lecture series, then you could get to things about gravity. But here, no. The question is what dictates how much the particles pull from the field. So far, as we're talking, we have a description of how much they pull from the field, and we have measurements for that. But what ultimately dictates how much they pull, we don't know.
Well, I can't say I wasn't entirely expecting that.
Yeah. But in any case, the only point that I'm showing you this is to say this from the high luminosity area, when we have 4 million Higgs bosons, is going to be a major pillar where we're going to be measuring all of these properties extremely precisely. And the second major pillar is kind of a diagram I've showed you in the past, is continuing searches for new physics. So like what we talked about last time, where we're searching for higher and higher mass particles, kind of the analogy, so I think I showed this a while ago, where if the Higgs boson is like the mass of a bike, we've probed up to roughly 15 times it, so like the mass of a Great Dane right now. And then from the high luminosity LHC, I tried to find something that was like 180 kilograms, and so it's like a sea lion. And so we're probing higher and higher masses and going from this guy over here to this guy over here. And so these searches are extremely interesting, and they're only doable because we have these very, very high energy collisions and because we have billions and billions of them. But of course, this is not all that there is in physics. The LHC is just one piece of it. And so there's tons of other really exciting experimental programs throughout the world trying to understand the features of all sorts of different particles in here. And so, for example, there is so-called B factories that exist, like this one Bell 2 in Japan, where what they do is they shoot in electrons and positrons, and they produce, instead of producing enormous quantities of Higgs bosons, they produce enormous quantities of B quarks. And then they study those B quarks to try to find if there's evidence for CP violation, things that could influence the matter-antimatter asymmetry, all sorts of exotic physics by producing tons of these. Then there's other ones, like, for example, there's experiments that study dedicated to the muon. So, like, for example, nearby here, actually in Batavia at Fermilab, there's this experiment that's turning on called mu2e, where what they're doing is they're measuring the rate at which muons decay to electrons, and they're seeing if that matches with the standard model prediction. And these are really interesting. Maybe you had heard not too long ago there was one called the G-2 experiment, and that one, I think it took its last amount of data and is now shutting down. And that one caused a big storm in the field because they measured actually a strong deviation from the standard model. Everybody kind of freaked out. And then years later, there was actually a big thing where the theory prediction was missing a crucial piece. And after adding in that piece, which I should say to them is extremely difficult, it is non-trivial by any means, then the predictions agreed. And so this experiment is studying muons again to try to push the limits of what we understand about them. And then there's this whole class of particles down here that I have not mentioned basically at all, and these are the neutrinos. And these, besides the Higgs boson, are kind of the particles we understand the least about. And there's a massive experiment being built called DUNE, where they're digging these giant caverns. And so this is actually what people will usually call as one of the next flagship US experiments. And so I just have one slide on here because I think that I'm going to guess this will be a future Compton lecture at some point just dedicated to things like this. But basically what this is doing is Fermilab, so here in Illinois, they're generating a beam of neutrinos. So they're shooting protons onto a target. Then we're getting a ton of neutrinos coming out. And then that beam is being shot through the Earth, 800 miles, underground through rock. And then it's being detected again in South Dakota. And so there you have a giant, what used to be a gold mine, now having detector electronics inside of it. You have detectors here. And what you do is you measure how many neutrinos are in the beam here, and you measure how many neutrinos are in the beam here, and between those two measurements, you actually get a lot of information about if neutrinos violate charge parity conservation, if they could account for the matter-antimatter asymmetry, and about the mass ordering. But I don't, yeah.
You see the oscillation?
Yeah. So the question was, will you see the oscillation here? So for more context, what exactly is happening is you create this beam of neutrinos here, you measure their species, and then through quantum mechanical processes, as they go, they oscillate between each other. And because you have a very long distance here, you give them enough time to really oscillate enough that you can detect how much they oscillate over here. And so you're really measuring that oscillation. Yeah. But in any case, I only have one slide here because I really think this will end up being an entire lecture series just on its own. Yeah, did you have?
I was going to ask how you focus neutrino beams since they don't interact very well with things, but that may be for the next hypothetical.
Yeah, and my honest answer would be I have minimal ideas of how you do that. People who really do this will know much better than me. But to emphasize again why I think this direction is interesting of measuring things more precisely and asking if there's more building blocks is in the end, everything that we're roughly talking about is understanding the building blocks themselves, which are basically the particles and forces, and then seeing if we can put them together. Like I tried to find a picture of a guy putting together Legos, and this guy built like a massive city of Legos that I guess cost him like $80,000 or something. It was crazy, but it looks really pretty. And so kind of this desire to measure these properties more and more precisely is in many ways akin to understanding each of these building blocks better and then seeing how they can fit together to form something complex like this, where you see tons of structure everywhere. You see structure on small scales, like, for example, cars coming by. You see structure on long scales, like the buildings, very much like we see blobs in the universe, whether that be dark matter blobs or large-scale structure like dark energy. And so this is really one direction. But then the second direction, which kind of links between these, is seeing if those blocks fit together. So this is something I showed in the very beginning, but kind of in a different format, is everything that we've been talking about is really all the way down here. So at the sub 10 to the minus 16 centimeter level. But everything that we really think about and interact with day to day is everything up here. So hadrons, which are like protons and neutrons, nuclei, which are bundles together of protons and neutrons, atoms that are bundles of nuclei. And so everything that we talk about is there. And somehow, at least to me, it feels like in studying these basic building blocks, I should be able to go like that. And so, of course, this is an entirely other area of research. And for kind of unfortunate reasons, it's kind of split between particle physics, and this is usually nuclear physics. But increasingly over, I think, the next 10, 15 years, these fields will really start to merge together again. And the experimental procedures that we're doing to understand them right now, it really fall into two categories. We either shoot hadrons and neutrons and break them together, or break them apart. So we blast them in at high energies and explode them, and then we study what the explosion looks like. Or we take effectively a microscope and we look inside of the nuclei as they're there, and then we see the dynamics that's happening inside. Yeah?
Every time I've seen that formula so far, it's always been E equals hc over lambda. And you've got h bar. What's the difference and why?
Oh, there's just, the question is this h bar or c, what is the difference between this and some other version? Yeah, h versus h bar, there's just a numerical constant between them. They're exactly the same thing, just with a numerical factor. Yeah. And so in the first direction, what people are already doing is smashing together nuclei. And so this is a picture at the LHC where two lead nuclei, so instead of one proton, you basically have 208 protons in a ball, both balls smashed into each other at the highest energies possible, and then you get an explosion like this. And if you look really deep inside here at the very earliest seconds, very earliest really femtoseconds, you have a state where the protons and neutrons are effectively melted. And you actually have access to what is inside of them. And so this melted state of protons and neutrons, you study that state. And this is happening at the LHC right now. And it's also happening here on US soil. This is an experiment that exists at Brookhaven in Long Island called the S-Phoenix experiment. And this is at a collider called the Relativistic Heavy Ion Collider, where here, instead of colliding lead nuclei, they're colliding gold. So this is two gold nuclei with now a mass number of 197 smashing together and again producing this kind of explosion. And so there's a big endeavor across the world to collide different nuclei species and study them. And so there's been lead at the LHC, gold at RIC, xenon at the LHC. Next year there will be oxygen. There's been deuterium, helium, and then of course protons. And in essence, what we're doing when we're colliding these different nuclei is we're creating different configurations for how those protons and neutrons inside meet each other. So if you have a bundle that is instead of 208 protons and neutrons like you have here, instead here you have around 200. And so when they meet, there'll be different configurations of forces, different ways that the protons can melt, different ways that the gluons can exist. And we're doing a systematic scan over all of those different configurations to try to map out how the quarks and gluons talk to each other and then eventually cool and produce the particles we see today. Yeah?
These figures, this one and the one that you showed before.
Yeah.
Are these figures or actually
Yeah.
a photo of what happened?
Yeah, so the question was this picture, the one on the right, right? The one on the right or the...
On the right.
Yeah.
And this one.
Yeah. Is this fake? Or I think did someone draw this? Or is this a real collision happening? These are real collisions. Everything that we've talked about so far, most of these lecture series have been about protons coming in and colliding. But a really remarkable thing about the LHC is using the same magnets, instead of injecting protons, you can inject nuclei. And so they really inject nuclei into the LHC, and these are two lead ions smashing together, and then all of these cells are pieces of the detector lit up. So exactly like everything that you've seen in the past, all the event displays like listed in the past where you saw vertical bars representing energy cells from the real detector, exactly the same, and this is a real collision. But of course, you can see from it, so much more complex. I mean, everything is lit up. The whole detector is lit up. It looks like a mini nuke went off inside of the detector and just flew outwards.
But this straight line with these figures here, it's incredible. I mean,
You're saying that these straight lines, like how this it looks like...
are these fakes also, or they?
Oh, maybe I'm understanding better. You're saying that these straight lines and like this look almost too good. These are what you're seeing here are not the particles coming out. These are the detector cells, which are physically, I mean, like a rectangle, for example. And that rectangle, which is the physical detector cell, a particle goes through it and lights up that cell, and then we plot that. Yeah.
Is there a name for this soup of melted protons?
Yeah.
What's it composed of? Is it got quarks and stuff just floating around?
Yeah, so the question is there a name for this kind of soup? One thing people call it is a quark soup. The more technical name is the quark gluon plasma. And it's exactly as this name describes. It's a state of quarks and gluons just sloshing around in a plasma-like configuration. And actually the name at this point, the name was given to it maybe 15, 20 years ago. Kind of misleading now, because now we have evidence that instead of being in a plasma state, it's actually in a liquid state. And we can measure its viscosity and things like that to get confirmation. And actually, so far as we know, it's the most perfect liquid according to viscosity and all sorts of other things that humans have ever made. So this deconfined state is extremely interesting. And I guess I'll say a few more words about why it's so interesting. Normally, quarks and gluons, you don't have them moving around freely. You have them bound inside of protons and then that inside of nuclei. But what you have here is really, for a small fraction of a second, quarks and gluons existing freely in a soup and moving around and interacting with each other, moving around. And so here you have a much bigger, effectively soup. You have a bigger slosh of quarks and gluons moving around, whereas here you have a smaller amount. And this picture that you're seeing here is exactly when one nuclei comes in like this, one comes in like this, and in the center region, it's really hot and dense, and you melt the protons and neutrons and create this plasma. Yeah.
In contrast to the two photons
Yeah.
hitting, where all the energy is in this thing that will create other particles.
Yeah.
Here the energy is spread, so the energy going to each one is somewhat less.
Mm-hmm.
So you get this plasma flat, so you're looking at how these things interact, and you don't get the jet structures.
Right. So the question was in comparison to the
Jets.
right, and so in comparison to the proton-proton collisions, where really you have a lot of energy pumped inside of a small area, and then that energy is converted to new particles that produce these really jet-like streams. And here it looks like you just effectively smash in a bag of stuff, and then all of the energy goes into making this plasma type. Yeah.
No new particles.
So here you're not searching for evidence of new particles. You're trying to measure this plasma. But what's important to see is that everything you're seeing here are particles that are produced in the plasma flying outwards and hitting the detector. Because the plasma is really on the femtometer scale. And so the name of the game here is all of the particles that you study in PP collisions, now you use them as probes here. Instead of really trying to measure properties of, for example, top quarks, you look at top quarks produced in here and how them interacting with the plasma modifies their properties.
I'm just wondering how you measure viscosity.
For example, measuring viscosity, you can look at the correlations between particles flying outwards and measure if there's hydrodynamics happening on the inside that then create a flow of particles going out in a certain way.
Create a hydrodynamic model.
Yeah, exactly. Yeah.
Have there been calculations as the temperature of the plasma at time of collision?
Yeah. So the question was, have there been calculations of the temperature of the plasma at the time of collision? Yes, and if my memory serves me right, it was something like 1,000,000 times the temperature of the core of the sun. Yeah, it's insanity. Yeah.
The size of these blocks.
Yeah.
Represents something.
The size of them has to do with just the physical size of the detector cell. The colors of them have to do with the amount of energy actually left. So you see lots of energy, these yellows, tons of energy on the inside, and then cooling down and getting less energy on the outside. But the physical dimensions is of the actual detector cell. So like in the calorimeter, you have effectively a box. Particles go through the box, and then what we're plotting here is just the box. Yeah. Yeah.
I've seen like a perfect liquid mentioned several times in physics.
Uh-huh.
What exactly dictates a perfect liquid?
Right.
So like superfluidity, does that count?
Yeah, it's exactly. So the question is, what exactly determines a perfect liquid here? When we talk about this, we do measurements of the viscosity and effectively determine if it's close to like a superfluid, exactly like you just said. Yeah. But okay, so I can talk to anybody more about this afterwards. But really, all that I wanted to mention is that this is an ongoing, huge experimental effort to understand how the basic building blocks that we've talked so much about then come together and form the nuclei around us. And this isn't the only one. So remember I said here that there's really two ways you can go. You can either smash them into each other and then study the soup that's made, or you can do effectively a microscope and have them sitting here and look deep inside. And so the other thing that's happening is at the same national lab that's doing these gold collisions, they're upgrading their experiment. So right on the end of Long Island, so this Brookhaven, they're upgrading their experiment where instead of colliding gold nuclei or heavy ions, they're going to shoot in a really high energy beam of electrons and a high energy beams of nuclei or protons. And then the electrons, which are point-like particles, are going to penetrate inside of the nuclei and effectively take a picture of what's happening inside. And so they're going to create a map of the quarks and gluons within the nuclei and protons and see how their configurations give rise to the properties around us. So this, I have the same reaction. I look at it, this is incredible. This is beautiful. And between both of these, I only put 2 slides of them because you could easily imagine an entire lecture series just on this, an entire lecture series just on this one, and then an entire lecture series on this one. So just to mention that this is a whole nother area that is equally as exciting as everything that we've been talking about.
This is somewhat less energy, though.
Yeah, so the question was, this is somewhat less energy. Yeah, so the beams of electrons, for example, are going to be coming in, I think the number is 80 to 100 GeV. So it's going to be a huge drop from the LHC. But to do this type of physics, you don't need those really high energies to produce massive particles. You just need enough energy so you have fine enough resolution to look inside of the nuclei. Yeah, exactly. Right. Okay, but of course this is only one piece of a growing story, which is also, we just talked about going from scales of 10 to the minus 16 centimeters to 10 to the minus 8 centimeters. And then all of that comes in on this diagram of the history of the universe and is just getting us to basically here. And then from there, you go this whole rest of the time, and all of dynamics of now nuclei are fitting together as the universe is expanding. And then if we take a picture of the sky, we see all these structures, and then seeing if everything we're talking about actually maps onto that. And the thing I want to say here is really that the links between, just as I said, the links between nuclear physics and particle physics are growing stronger and the fields will progressively mold back together. The links between astrophysics, cosmology, and particle physics are also growing stronger. So for example, a lot of our motivations now are really from cosmological measurements. So for example, dark matter from a particle physics side, this is purely, the experimental evidence is purely from looking up at the cosmos, taking pictures of the sky and seeing if it matches the calculations. The matter-antimatter asymmetry that at the LHC we do tons and tons of searches to find tiny particles that could lead to this is in itself a cosmological measurement. It's again, you look up at the sky and you see what is the rate of various nuclei that are up there. And then a third one is in astrophysics, for example, an increasingly intense study of various star systems. So for example, like neutron stars. For example, at Dune, they'll be able to measure neutrinos produced in stars flying towards us, and then underneath in their giant detector in the gold mine, seeing those neutrinos come from the stars and infer things about the stars. But from our perspective, inside of these neutron stars, for example, deep in the core, you could imagine the temperature is very hot. There's tons of particles around. And as it turns out, the material that is in there is basically like the material that we produce here. It's exactly like quark gluon plasma. And so measurements that we do here, information from astrophysical sources about neutron stars, all of them are blending together, and you're learning a lot throughout. And so I just wanted to give a shout to another US flagship. So I've talked about Dune, which is a large-scale experiment. There's the Electron Ion Collider, a large-scale experiment. And then this one, which is the Legacy Survey of Space and Time. And so this I mentioned in the past. It's the biggest digital camera ever made. So for example, this is a person here, and this is their camera. Massive. And then they take this. So this was built at Slack National Lab in Northern California through an international effort. This was then shipped to Chile, where the atmosphere is really clean and you get really high resolution images of the cosmos. And there's an observatory where they took this, mounted it inside here, rotated it like this, and just, I think maybe even 2 weeks ago, they took their first picture to actually start calibrating the camera. And so what this will do is over 10 years, they'll take pictures of all accessible places in the sky, and they'll learn about dark energy, they'll learn about dark matter, they'll learn about neutron stars, they'll learn about all sorts of different things. And so from the particle physics side, because all of these are really motivation for us to search for small scales, particles that can lead to these big scale behaviors, anything they learn, we need to keep our eye on because they will be directly relevant to our searches, our measurements, everything that we do. And again, only one slide here because I'm pretty sure this could be an entire future Compton lecture also. But what I hope is also clear is that in doing these different types of physics, what we're doing is we're building extremely large scale projects. We're going from, instead of in the basement of a lab, we're going to a telescope in Chile, a 27-kilometer ring, an underground experiment over 800 miles, in this case, 10-kilometer ring, really big scale experiments. And so when I think about these different things in the future, the inevitable thing I end up to add is what is the timeline for this? How long are we actually talking? And this is a plot that to me actually kind of scares me somehow because people really now talk about all the way out to 2070. And I'm young, so I look at this and I go, what the hell is going on here? But roughly the timeline is that we're somewhere right here, and the high luminosity LHC will turn on sometime end of the 2020s, so maybe 2028, 2029. Then that will run all the way up until roughly 2040, 2041, and then I will come in a second. And then as that's running, the legacy survey, so this one right here, will be running for 10 years there. The electron ion collider will turn on around 2030 and run for around 5 years. And then in the midst of all this, we'll have all the other experiments, the B physics experiments, the neutrino experiments, the muon experiments running also. And so roughly these 4, high luminosity LHC, DUNE, electron ion collider, and the legacy survey will somehow take us anywhere from 2040 all the way up to mid of 2050s. So the experiments that we're building right now are really, for the young people, is their entire careers in principle. And so then you can ask, well, for example, the LHC was conceived of in the 90s and then really got built in the 2000s. So if you're a young person in this field and these experiments were already designed, then you need to think about, well, it would be nice for me to get to see a design also and contribute to a design also. And so then you're really talking about 2050s onwards and even later than that. But of course, the question was, how old will I be in 2050? Well, I just turned 27. So, like 2 weeks ago, I turned 27. So, thanks. Yeah.
Well, in 2061, Haley's comet comes back. 113.
Yeah. So then, instead of doing all this, we'll just look at the comment, and we'll do that. Yeah. Yeah. Oh, see, you may do all of these experiments, actually. Yeah.
Well, I'm more curious now. I'm wondering about dark matter. It's like partially from the last lecture.
Yeah.
You mentioned dark matter. Could like the particle that we talked, the unknown particle last lecture,
Yeah.
be dark matter? Is that a possibility that has been explored?
Right. So the question was, we've talked a lot about dark matter, and last time we talked about searching for hypothetical particle, and could that one be dark matter? The one we talked about last time, the idea is that one wouldn't be, but similar ones to that are searched for really extensively, and so we've been doing that all the way from really the past 20 years. And kind of the two areas you need to have in your head is, are we trying to produce dark matter ourselves, meaning do we shoot in a bunch of protons, produce an energy source, and then see dark matter come out? Or do we look for dark matter coming from the sky and just indirectly measure it? And so that's kind of the two directions. So there's the LHC that's doing one, and then the other one, not to disparage all of that research, but kind of what it is you put a giant vat of liquid, like liquid argon or something like that, and then you wait for things to come and hit it. And those things that come and hit it are the dark matter. Okay, that's very simplified, and I'm sure that they would punch me for it, but that's roughly what it is.
So
Yeah.
could they be like a different generation of particles?
Yeah.
Like particles in the universe?
Yeah, so the question was, could they be an entirely different generation of particles? They could be, at this point, it could be anything. They could not exist. If you look at, I've never put a plot up there, but if you look at the order of magnitude that people search for their mass, it's spanning like 30 orders of magnitude. And so it's a really massive search space, and it could be tons and tons of different things.
Isn't it true that the only evidence for dark matter is Vera Rubin's measurements of the galactic rotation?
So his question was, isn't it true that the only evidence for dark matter are the galactic rotation curves? I think that is a strong version of evidence. I see you giggling. You want to get me in trouble. No, there's also, there's a gravitational lensing where you can look at up in the sky and you see light that's bending around at a giant body of mass. And if we look at it and we don't see anything there, we indirectly infer that there's dark matter.
Be a halo.
Yeah, that there's got to be something. I think maybe the more direct answer to that is, so far we have indirect evidence of dark matter, meaning we look up at large scales, we see certain phenomena, whether that be galactic rotation curves or lensing, and then we infer that there needs to be a new mass source there. Yeah, yeah, yeah. But so everything I've talked about is taking us up to roughly around here. But of course, you see these other lines, and probably something you've heard about in passing is the talk of a new collider, a bigger collider. And so I have one slide that's kind of mentioning the four main things that people talk about. There is at CERN the Future Circular Collider proposal, where it's a 100-kilometer long tunnel. And so for reference, this little tunnel you see here is the LHC. And then this tunnel here is the proposal. So massive, massive. Yeah.
Getting back to those dates, Venus comet just passed its highest point a few months ago. It's a Badea point. The previous one, during that week, I was born. So I'm close to 76 years old. Also, during that week, the first successful prediction of a tornado occurred.
Okay.
March of 1948. First time a tornado was successfully predicted.
Wow. That's crazy. Yeah. Did I see another order? Okay. Yeah, so just to walk you through the different proposals, there's this one where, again, this is the LHC, and then this is the proposal. And here, kind of the two directions for all four of these is one, to do precision. And so when we want precision, we shoot in electrons and positrons up till now, because they're point-like particles. Whereas when you shoot in protons, they're bags of quarks and gluons. And them being bags, there's an extra uncertainty there. So we shoot in electrons and positrons. But then if you want to get to really high energies with them, they start radiating a lot, synchrotron radiation, as they go in a circle. And to counteract that, you need a bigger and bigger tunnel. And if you work through the math for what we want to do now, roughly the tunnel that you need is 100-kilometer long. And so the idea is to do a staged experiment where first you build this tunnel and you put an electron-positron collider. And then after you run for 15 years or something, you upgrade it and put a proton collider inside the same tunnel. Though this picture of a 100-kilometer long tunnel may look unreasonable, the idea of building an electron-positron collider and then upgrading it is not unreasonable. That's exactly what the LHC is right now. Before the proton-proton collider, there was an electron-positron collider in the same tunnel. So that's roughly the proposal. And at the same time as Europe is proposing this, China is also proposing almost an identical experiment on Chinese soil. Everything I just told you, almost identical. And then in Japan, there's a proposal for, instead of a circular collider, you have a linear collider. So just two beams going like this. The interesting thing with this is that because they don't go in a circle, you don't have the synchrotron radiation from particles moving in a circle like that. But on the other hand, that means that you don't have a ring where you can cycle particles many times in a circle so they can get to really high energies. You just have one shot. And that also means you only have one collision point. Whereas everything that we've talked about at LHC, you have 4 collision points, 4 experiments, 4 different dedicated experiments for different things. Here you would only have one. And then the last one is an old idea, but kind of reborn recently, is the idea of, instead of colliding electrons and positrons or protons, you collide muons, so the heavier version of the electron. And the benefit here is that instead of having a 100-kilometer long tunnel, to get roughly the same physics, you could have a 10-kilometer long tunnel that would roughly fit inside a Fermilab. So I think what I would say here is that my opinion on all of these is that the earliest of them is roughly 2050. So I personally don't spend that much time thinking about these. I want to work with the current experiments and see what we can learn now. But there is active, heated discussion about these, because historically to get one built, it takes roughly 20 to 30 years. And if we want one built roughly when the LHC ends, which is 20-ish years, you need to start working now. And so there's reports that are coming out. In the US, there was a report that came out that actually gave strong favor for this one up here. The Europeans are putting together a report right now that should come out in roughly a year, and end of 2025, and that will also weigh in on these. And so there's active discussion. Just for me, this is a bit far away to really invest a lot of my time in doing. Yeah. The question is, what's it going to cost $1 trillion? I think that the scale people talk about, I know the numbers for this one better, something like 20 to 30 billion. Yeah, I guess it's cheap. I have to say that's not the response we usually get. So maybe you go talk to some people. And, yeah, so it varies. I think the hard thing is for something of this scale, it's bordering France and Switzerland, but really this is an international, I mean, to build something of this scale, it's an international project. And to get so many different countries to buy into something, especially if it's not on their soil, adds a lot of complexity to it. Yeah. So I try to stay away from the political conversations and do the science, but yeah.
Are the leptons considered structureless?
Right, so the question was, are the leptons considered structureless? Yeah, so this question is exactly crucial to this. The answer is, so far as we know, they're point-like particles.
So you can use them as a pole.
Yeah, so they can be shot in, and you know exactly their momentum because you produce them with that. Compare that with, for example, protons, where they're a bag of quarks and gluons. When we shoot in a high-energy beam of protons, what we're actually colliding is what's inside the quarks and gluons, but because it's a bag, we don't know exactly the momentum of the quarks and gluons. So there's an uncertainty in even the initial process of shooting two things in. You don't have momentum conservation in the launch, in the plane coming like this where the beams are coming in, because you simply don't know what their momentum are because you didn't shoot in the quarks and gluons, you shot in a bag of them. Whereas with electrons and positrons, they're points, and so you can really shoot them in precisely. And that same reason is exactly why for the electron-ion collider, they're using electrons, because you can measure, you know their momentum very well, and you can shoot them in like probes.
The same is true for muons.
The same is true for muons, the same is true for taus, and roughly the logic goes for muons, why it's smaller is this synchrotron radiation. It goes like 1 over the mass to the 4th. And so if you have a really light particle like the electron, the radiation is really intense. And so if you now go to muons, which are 200 times heavier, the radiation goes down a ton. And so you really can do a lot more with it. But I would say this technology, compared to these, really in the really early days of this. I would say that this, if someone dug a tunnel, we could probably build this now. Maybe plus or minus some time to get magnets and stuff. Not the proton version, the electron-positron. This could be built now. In fact, this has been talked about for, I think, 20 years now. So you could build it now. And then CPC, very similar, you could also build it now. Yeah, it's like SLAC used to be. The question was this one in Japan is like what exists at Stanford, the national lab next to it. They used to have an electron-positron collider like this, and now they just changed it so it's a photon source. They shoot in effectively an electron beam, and then they get high-energy photons coming out, and then they use it as probes to effectively image molecules or atoms or all sorts of different things. But yeah, so I think this is, 25 years away at the earliest. And talking about other long-term projects, other proposed projects that people talk about, there's the idea of a third-generation dark matter experiment. So roughly the language here is people use third generation or stage 4 to, in some way, shape, or form, mean bigger. So for dark matter experiments, there was a first generation where, again, in simple terms, it was a vat of liquid. That vat was very small. So the likelihood that something coming from the sky was going to hit a small vat was low, and now they start making the vat bigger and bigger and bigger, and the proposal is to make a really massive one, where actually you'll be able to do dark matter studies, supernovae studies, measurements of particles coming from the sun, neutrino measurements, so really bigger purpose, but also big scale. And then there's also a proposal to put a new detector in this poles to do measurements of the cosmic microwave background. So these are photons coming from the early universe. As they flow towards us and the universe is expanding, their wavelengths are getting longer, and then we can actually measure them here on Earth. This one, actually, I just found out recently that the prototype for this detector is actually maybe like a half a mile from here in a warehouse that people are testing right now. A challenge with this one is, well, you actually have to get to the South Pole. And the planes to get you there are military planes that need to land on a very particular type of ice. And supposedly the planes are being decommissioned. And we need new planes to actually get the science there. But of course, they don't care about this. Their focus is getting planes there for other reasons. And so this, though the science case is really good, there's a lot of questions right now of if this will actually happen. But to connect to the next part, so I know it's almost noon, but I wanted to go, if people will sit around for maybe 10 or 15 more minutes, to talk a little bit about the technology side. So clearly in all of this, this is very large-scale experiments, and you're going to need technology to do it. And the two things I wanted to talk about just quickly were on this pyramid, the things that I personally am thinking more and more about now, which is something called distributed AI, which is in this narrow category, and then AI for science, which is in this general category. And so I'll just do a quick check. Are people okay? Keep it going for another 10, 15 minutes? Okay. So this idea of distributed AI, so we talked, if you remember the triggering lecture where we talked about how the data was being flown effectively off the detector into dedicated electronics like FPGAs or different things like that, and then you had algorithms running on those to actually make decisions. The idea here is because the data rate is so high, you can't actually transmit all of that data in real time. So what you need is you need computing on the experiment itself inside of the detector hall, right next to the collisions, to do analysis in real time. And what this requires is a mix of AI and microelectronics. And so to say in different words, if this is a plot that roughly shows the amount of computing time that you have, so down here is nanoseconds, and this is 10 seconds right here. And then up here is approaching like a petabyte scale, and then all the way down here is kilobyte scale. And the LHC sensors are all the way up here, petabytes of data per second, where you have nanoseconds to actually make decisions. And if you compare that with everything else like plasma control, nuclear reactors, Internet of Things, mobile devices, the needs are really much, much greater. And to actually accomplish this and use all of the data, you need these microelectronics. And to say, again, to reiterate again, this is a slide from I think it was the 4th lecture, where in our current decision making, where we throw out 99.75% of the data, we don't use the data from the innermost piece of the detector. The most sensitive parts of the detector, for the momentum, we don't use it at all. And we make decisions that those decisions then result in discarding data. Now that data is usually background, but there's chances that it actually contains physics we're interested in. We don't use it at all. And so the idea, the nutshell of the idea is if you look right at that detector level and ask what's happening, in effect, you have particles moving in a magnetic field, and they bend. So high momentum particles come straight like this, low momentum particles bend like this, and as they hit the sensor, they leave hits along it, and in doing that, they leave very distinctive patterns. And so the idea is that you put a piece of hardware, a chip right here, that connects directly to the sensor, that analyzes the data in real time coming off of it and makes predictions of if it's a high momentum particle or a low momentum particle. And this chip, to reiterate how difficult this is, the chip needs to make these decisions at 40 megahertz, so 40 million per second, and it needs to be extremely radiation hard, meaning that if you put it next to all of these collisions, tons of particles will come flying out, which means that they'll hit the electronics and degrade the electronics over time, and that they can effectively break over time. So really radiation tolerant. And this is actually, the picture that I keep showing you is designing this chip exactly. And so this is nearby at Fermilab, where that core idea of making measurements of the momentum and predictions if it's high or low momentum is now actually taped out on a 1.5 millimeter square chip. And that chip is underneath that gray thing right there. And so underneath that gray thing. And what it is that on the chip, there's a bunch of little pixel sensors, microns big. The data from those sensors come together, and then we actually make decisions like this. And so this general idea of putting an AI algorithm onto a piece of microelectronics and putting that inside the detector and doing effectively data reduction at the source instead of much later on is something that people are really pursuing. And so this is really early days for this. And there's a lot of questions going around right now of what new doors will this open in physics. I think people don't really know all the new opportunities. To me, it really feels like you're for the first time allowing for more complex decisions earlier on. And so there's obvious ones that are what will happen at the LHC colliders or future colliders. But then there's other experiments, like for example, the neutrino experiments, where they have very similar types of pixel sensors, high data rates, and you could imagine putting similar types of electronics nearby. And so this is kind of the first direction. And to emphasize, in that long timeline that we've been talking about, to get to the experiments that we want, these type of studies are really needed now. And so that's why, for example, this chip that we're designing here, maybe it will get installed in the LHC in 7 years or so, but more likely this will be for a far future detector. And then the second thing I wanted to just highlight is this AI for science idea, and just tell you maybe a little bit more about where my head is at on it. So a major goal in this is just accelerating breakthroughs in science. So if you remember back to the lecture about simulations, where we had all of these ideas of actually taking the set of equations, running them through computing models and getting predictions, with the new technologies, you could imagine doing that in a far more automated way. And so roughly, in my head, what this is saying is, can I have an AI that solves all of the physics questions inside all of the textbooks that I had to study as a grad student? So it solves all of those, and then it goes one step higher and looks at all of the current research and understands all of that, and then it actually makes predictions. And so this, though it sounds kind of outlandish, there are current attempts to do this, and the curiosity here that I just wanted to let you in on is if the current paradigm will actually take us to this place. And I see, do you have a question? Yeah.
Yeah, so what is the problem with putting just like a simple like micro transmitter in there? Or put it like get mixed up with the background of the accelerator?
You mean?
Like a little transmitter sends like the data over.
Yeah.
Like very quickly gets processed by a much larger thing and then sent back.
Yeah. So the question was, what's the problem with having some little microprocessor or something where the data gets shipped from the detector to that, where it's a more powerful system? Yeah, you do the analysis and then you ship back. That's exactly what we do right now. The problem is that the data rates that we're producing is even too high to go through those cables. And so we actually can't even process all the data in real time. And so then the idea is put it even closer.
I mean wirelessly. Like,
Oh. Yeah. Yeah, it sounds nice.
AI remote.
Yeah, so the question was, what about wirelessly? It sounds nice. There's work towards that. But maybe let me just paint a picture of what that really looks like. That looks like you produce data in here. Bearing in mind, producing data is a bunch of particles flying out. And then you're saying take that data and transmit it wirelessly. Transmitting it wirelessly means shooting photons. So more particles being shot out. And the amount of all of that together in one area sounds great, but sounds very, very hard. And one day maybe it'll happen, but right now we're not quite there.
Yeah?
Yeah.
It'll get mixed up with the background parts.
Yeah, yeah. But if one day you invent it, then come and come and give it to us. Yeah, yeah, yeah. But right, so the thing I wanted to mention here is the current paradigm. The question in my head is just how far it can take us. And for reference, the paradigm, I'm not sure if people have seen these things, but roughly what's happening right now is this so-called scaling hypothesis. And it's kind of a simple idea, but was actually demonstrated in this paper from a while ago, actually by one of the people I put the quotes up for. Roughly all this is that if you have neural networks and you ramp up the amount of computing time, so you train them for longer, you ramp up the amount of data that they take in, and you make them bigger, that they will get better. And what they did was they actually did studies of that where along this axis here is the amount of computing time, along this axis here is the amount of data, along this axis here is the size of the model, and this is the so-called test loss, which is how wrong are the models, and you see these linear trends of them just going down. And this exact idea of just make things bigger has translated everywhere into massive computing facilities where people want bigger computing, more data, more training times, and just this core idea of scaling things has translated now into billion-dollar facilities like the Microsoft Azure facility, and in a few years the projections that it will be $100 billion facilities. And to emphasize, this is really an empirical observation that if you look at the neural networks we train, you have scaling laws, and it's a trust that these scaling laws will continue like this and won't level out like this. And so then you can look at how well these models are doing on math and physics. And these are really, really recent results. So in comparison to in particle physics, where we're talking 20 years to accumulate the amount of data, here we're talking this year and next year, really fast results. And so this was a plot that I could get. I couldn't understand why they made everything so light, and it's very hard to read. I didn't understand this at all, but this was the plot. So basically, this is a company called DeepMind, which is a company that's joint with Google. And so they made a very large model and had it compete in a competition called the International Math Olympiad, which is roughly the hardest youth math competition. So people that do this usually end up going on to be math professors, field medal winners. And so they had their algorithm run, and it scored right here, just on the boundary of silver and gold medal. So to emphasize, this competition is, I think it's something like the best 4 or 5 mathematicians from every country go somewhere and compete. And they had their algorithm run on it, and they got basically a silver medal. And to emphasize, this is really their first time at even trying this. So I'm going to guess that next year, instead of having a silver medal, they're going to have a gold medal. Now, inside of this, there's details that are hidden. Like, for example, that to actually do the test, people have 2 blocks of 4.5 hours, whereas the algorithm for one problem took 14 seconds and for another problem took 4 days. So there's some more details in there that need to get worked out. But for this, it already seems very impressive. And then from a physics side, a different company, OpenAI, which is a joint now with Microsoft, they had a similar algorithm, but trained and evaluated on PhD level problems from chemistry, physics, and biology. And this result is actually, I think, even a month and a half old. I think this paper is from mid of October. And they had it answer these questions. And so this is their previous model where it got like 40%, 60%, and 60% on chemistry, physics, and biology. And now it's at something like 65% chemistry. I think they prioritized physics a lot in their design, and they got up to 92%, and then 70% for biology. Now, of course, the question that you should be asked is this even reasonable? What questions are they actually testing on? Are these really PhD level questions? Everything that I can tell, they're really roughly PhD level questions that you would take in the early parts of graduate school, and they evaluate very quickly. So this seems really impressive. But again, all this relies on the idea that if you just scale things up, that things will get better. But the reports coming out now from the companies that really have access to this amount of compute is that the scaling laws are starting to slow, meaning that this line here, instead of continuing like this, where if I just ramp up compute another order of magnitude, I build instead of a $1 billion facility, a $10 billion facility, and everything gets better, now it's starting to level off. And that means that just building bigger and bigger won't necessarily translate into better and better compute. Which is really, really important, because that means that you effectively will need some new innovation to keep going with what people are doing, because the current ideas just won't go further. Yeah, so the question was, is this because of the classical computing, and is quantum computing factor in here? This is entirely classical computing. But to go even further than that, there's not even really like good theory for why this happens. This is purely an empirical result, meaning they took a model and they just made it bigger, trained it, and then got a data point for how good it was, and then put that on a plot and fit it to a straight line. And that's it. And so that was a very good connection. So, because I wanted to mention the two wild cards in all of this is one, if there will be new hardware computing, so whether that be new chip developments, like NVIDIA is putting out these dedicated chips now that they report are something like 30 times more performant, 25 times more energy efficient. And so going from a small chip to a big chip like this, and then the other elephant in the room is if somehow somebody gets a really functioning quantum computer, everything that we're talking about, these scaling laws, all of these could break. But so in any case, the whole point I wanted to make out of this entire lecture was that, to me, I think without a doubt, the intersection of particle physics and nuclear physics, keeping an eye on cosmology and astrophysics, and AI and electronics will be an extremely fruitful line of research for the foreseeable future. We'll understand more about the building blocks, more about putting them together to form large scales, and using technology in between. And so with just my last 2 minutes, I wanted to first say, again, thank you to the organizers, and I wanted to, if we could have a round of applause for Mary up there, who comes around. And then I'm going to have one more round of applause, actually for you guys. And so it's been a really great pleasure actually being here. I've learned a lot, and it's been really nice to meet all of you. So I wanted to have one more round of applause for everybody here. And thank you for coming to everything. So that's all I have. I'll stick around for really as many questions as you want, but thank you. Yeah.
You know, I saw this movie, breaking down that
An Enigma. Oh,
okay, but let me just say,
the World War II movie? Yeah.
yes, which really find out all these codes that the Germans were using, okay, between submarines and whatever.
Yeah.
And then finally, they were really, the problem was the amount of computing also in that area.
Yeah.
Okay, how much? And the machine goes, it reaches one point and stops.
Yeah.
Because it cannot compute any further. And then finally, they figured out that every message ends with Heil Hitler.
Yeah.
And then that one thing,
Yeah.
by figuring out this one thing, reduce the amount of computing
Yeah.
for data. Okay, they really reduce the number of data so much.
Yeah.
Okay, which makes it possible to really compute. In this case, this reminds me that if we find out
Yeah.
something common that controls the behavior of all the particles together,
Sure.
okay, do certain hypotheses.
Sure.
1, 2, 3, 4, 5.
Sure.
And then use them there, you may find out that you really can reduce the amount of data you need to compute.
Yeah.
That's only,
You could be right. Maybe I'll repeat. In this movie, and in long in computing, oftentimes there's just one little insight. In that case, it was this single message that unlocked all the code that rapidly reduced the number of computations. Could something similar happen here? It's extremely, extremely possible. And I think the idea is that if these scaling laws really do level out like this, we won't make significant more progress unless we get something that changes the way that we do these computations, rapidly reduces them, something. Similarly, on the particle physics side, I mean, you could imagine when we start doing the high luminosity of the LHC, that we need equally amount of the simulation. And from that other lecture, you have to do all these Feynman diagrams, computing all of them. And this takes tons and tons of time. And now people are coming up with different ways to compute the diagrams, saying, forget about the diagrams, I do something else. They use a deep insight that they found in computing things much faster. So it will be needed. I don't know what the answer is, but you're right that something needs to happen. And next 10, 15 years, probably something will happen. Yeah.
Back in 1964, Peter Higgs came up with ideas about the field that came from the now, shouldn't he have been
Yeah, so the question was back in 1964 when Higgs was coming up with the idea of the Higgs field, should he have been able to make some prediction about dark matter because if dark matter has mass, it probably got it from the Higgs, and then something along those lines. First, at that point in time, dark matter was not really known. There was ideas, I think, floating around. The timeline is a bit hazy in my brain. But also, more than that, he could have made a prediction for introducing mass to new particles, and plenty of people have made these predictions, but none of them have turned out to be true. So people have tested all sorts of ideas of does dark matter get mass from interacting with the standard model particles. So far, we have no evidence of it. So next 10 years, 15 years, maybe people will know.
Build another accelerator.
Yeah. Well, if you want to come and tell people that 30 billion is is cheap, then
It's about 2 fancy nuclear submarines.
hey, that sounds pretty good. Yeah. Yeah. Let me come up there and then I'll come down. Yeah.
So if the AI does scale up, does that mean a lot of years we switching to experimental physics in the future?
If the AI does scale up and it gets good at doing all of this, does that mean that they'll switch to the experiment? I don't know. Because you could easily imagine then that all of our analysis of the data, like where we write code to analyze the data, if it's really so good, maybe it just writes the code and analyzes it itself. I don't know. No idea. Maybe the more real thing is the skill set that people are trying to, that I think is worth getting. I think it's really important to have the hands-on skill set to actually go and physically build them. Because if everything you project in your mind will be done by computers like this, actually physically building it, I think the time of having robots come and build experiments of this scale are much, much further away. So physically building stuff, I think, is really important.
Does that take the fun out of it if you can't imagine and come up with ideas like
Yeah.
making predictions about what the theory should be or the way the Earth behaves?
Yeah, so if it takes the fun out of it, I don't know. I'm currently having a lot of fun envisioning that I could have a system next to me that when I'm working by myself, I can like talk to it and it gives me, I bounce ideas off of it. This sounds really fun and nice to me. Maybe in 20 years or something, it'll just say, I don't need you anymore, but, but for now, it's nice. Yeah,
There was this flyer for the Sievert lecture series,
yeah.
and it's gone now. I wonder if someone could give us the website where you could find it.
Yeah, so there's,
Department at Northwestern.
so after this, I think we'll write up, once Mary gives me the thumbs up or thumbs down to stop, then we'll put it out. Yeah, yeah.
Wouldn't this, for right now today, be beyond the scope right now? Because the amount of computing power that it would take, the amount of storage it would take to know all this and keep that together and quiz itself and, it's impossible today.
Yeah, so the question was, shouldn't something like this be impossible today because of the amount of computing, the amount of storing of data, all of these things? I would say maybe 5 years ago, people might have thought more like that. Now, I mean, I put it up just in passing, but a result like this, where it's solving really complex math, I mean, the rate of acceleration of the tools, I think, is beyond what people really thought would happen. And I mean, something like this, where they're really claiming that on physics PhD level problems, basically, I mean, effectively what this is saying is that you reach 100%, and then you're like a graduate student who's taken all of the classes and now is transitioning to research. And me personally, I think once you reach the $100 billion computing facilities, you'll probably start getting things that are potentially research level. Yeah. Now, I think there's a big gap between having a system that has the expressibility to do something like that and realizing that it actually makes contributions to the field. I think there's a gap there. You know what I mean? Like there's a gap between it can solve problems and understand the research and maybe produce small things, But to make something that is really a big game changer, yeah, I think that will require much more. Yeah, yeah. Yeah.
I'm trying to wrap my head around this, and I'm having a hard time.
Yeah.
So you have these systems that solve these kind of problems, but who's putting the problem to them? I mean, there's like a human control here that I don't see how there's any way you're ever going to escape that. The computer, are these models ever going to evolve to the point, you think, where they're going to, the problems to be solved will occur to them, and then there is no longer any need for any human input?
Yeah.
I mean, you're deciding what to use these for.
Yeah. Yeah, so the question was, we're inputting ourselves into it, what questions we want it to solve. Will one day it go out and actually decide what problems to solve? So for these, 100% agree with you. What we're effectively building right now is the best calculator ever made, where you can compute everything in the textbook, solve everything. But there's early versions of the idea of having these systems basically do exploration and actually come up with problems to solve. Here, and I think at Argonne, there's a lab where they're synthesizing materials and chemicals. And what they do is they have a robot in the lab that moves over to the test stand, actually does the experiment, then goes and computes the result of the experiment, sits there and understands the results, and then comes up with the next experiment that it's going to do on the lab. And this exists now. People are doing this now, right down the street. So it's kind of outlandish to think about, but this paradigm of bigger, these scaling laws, things like this have really shown to be very powerful. And now if I go and take it outside of, I told you about a very confined space where you imagine it's a room like this and a robot goes back and forth. If you start talking about a giant particle experiment or something like that, then you need physical systems that can interact with the world. But this idea of taking this from something where we tell it what problems to solve versus it explores and solves problems, learns from it, and continues exploring, I don't think that's as far away as people think it is.
The solution to the thing ever turning around and telling you I don't need you anymore is the solution to hell in 2001. Just pull the plug.
Yeah, and we could just handicap it. I don't know. The thing with the handicapping it, like, I would love if me sitting there, okay, at least for me, the best thing is to work with people that are much smarter than me and who know much more than me. And if you have a system that is much smarter than everybody and you can learn from it, to me that sounds exciting. And I think that line of thinking people won't handicap these systems. I don't think people handicap them. Yeah. Yeah.
My opinion on handicapping them is they shouldn't handicap its intelligence, they should handicap what it can do. You can't just tell humans, I don't need you anymore, or I'm not going to teach you anything, I just want to do it myself. That's what I think should be handicapping, as opposed to that intellectual.
It sounds reasonable.
And maybe, we could maybe handicap its ability in computer science.
Yeah, it sounds reasonable. I think when I start going down that line of thought, it gets hard for me to figure out how to create a rule system for for what things to handicap or not. And then also kind of the scientist inside of me is curious just how far can these things really go. And then as soon as that enters, I just want to see what it can do. And then I don't handicap it at all because I would like to see, I don't know, can it really spit out an equation of everything? Is that really possible? I don't know. So I don't know if I would handicap it, but it's a good point. Yeah.
Do you think that, given where AI is going, what we're talking about, is being able to determine problems and where direction should go on its own, does it make more sense to put your dollars and cents there when we're looking at all these experiments about nuance and the large collider and all the money that's going to take?
Yeah.
Does this allow us to maybe say, don't go here, go there?
Right. So the question was, you've seen now two, almost like these could have really been two different lectures probably, of a whole view of physics and then a whole view of AI. And how do you decide where to allocate resources, either my own time or the community's time? Should we build these big things? Could the systems inform us about the decisions? I would say that maybe contrary to the most recent thing is that informing the experimental decisions of what experiments to build, I think we're not there yet. From a researcher's point of view, at the intersection of them, it's a real open question of what is the most worth it to spend time on. I personally have the feeling of that the big questions about the universe and about physics really relies on frontier level physics research. But man, these systems are getting to a point where you got to think, should I invest 100% of my time just into doing things like this if the acceleration is so fast? And I personally don't have a good answer. I kind of struggle to figure out how much time to allocate to different things. But it's certainly a challenging thing. I mean, if you're like a funding agency, for example, and you're debating where to put your eggs, tough. You have a field that's really exploding, new results every 6 months, versus a field where the results are 20-year timescales, things like that. But I think the thing that I would say is that the 20-year timescales, I think you're asking a much bigger question. I mean, everything we've talked about has boiled down to, 18 particles? All of physics into this small amount. And so inevitably, to get one level higher, it's going to be a bigger endeavor. And so at the timescales that we're talking about, that endeavor still feels worth it to me. Now, the AI endeavor, I think you'd be kind of silly to not be paying attention to it and spending some amount of time looking at it. Yeah.
Is DeepMind just a super duper classical computer?
Right.
There's no.
Yeah. Yeah. So the question was DeepMind just a classical computer? So DeepMind is is the name of the company that is doing this version of it, and all that they use is giant computers, classical computer systems, where quite literally, I mean, I think I've said it a few times, but just to emphasize, this is, you go and you buy 10,000, 20,000, 30,000 graphics processing units that you could buy at Best Buy, and you hook them all together in a line, and then now you have a supercomputer, and that's what they use. Exactly that. Yeah. Okay, I think Mary's giving me the thumbs up. Okay, thank you, everybody.